As you know, the LHC collides both protons on protons and lead ions on lead ions. And possibly it is good to discuss first the different motivations for these two programs. In the case of a proton-proton collision, the idea is to deposit as much energy as possible in as small a volume as possible. The idea is that energy equals mass, E equals mc squared. So by depositing as much energy as possible in a small point, one has a chance to produce particles, elementary particles of the highest mass. And that has allowed, in fact, over the last 2 years to find first indications for a new, very heavy fundamental particle, a Higgs-like boson. The motivation for lead-lead collisions is different. There you collide really extended objects. And the idea is to deposit a high energy in a sizable volume so that essentially you start cooking matter in that volume. So you do not want to produce new elementary particles. You want to understand how the elementary particles that you know interact with each other, how they form matter properties. And for that you use lead ions because lead ions are very extended objects. So now you ask, what have we learned from these two collisions? Well, in one of these lead ion collisions, in a single collision, we produce at the LHC more than 20,000 charged particles. And we can study their debris. And by looking at all these particles, at this particle debris, we learn about how this medium was formed. And in fact, we find, first of all, that there is a medium. All the particles that are produced seem to emerge from a common flow field. And we can go as far as specifying the properties of that fluid that was produced in these collisions. So we have confirmed in particular that this fluid is a much better fluid than water, in the sense that it flows with much less viscosity than water. In addition, we can embed extremely high energetic objects into that fluid, and we can see what happens to these objects, essentially to what extent they can escape that fluid. And what we find is that this fluid is extremely opaque to highly energetic objects. So they don't make it out, or they make it out only by losing a large fraction of their energy. So in the future we think that this stopping of very specific high energy objects in this fluid can help us to learn more about this exceptional matter produced in these collisions. This is a crossbreed between proton-proton and lead-lead collisions. In this case, what you do, you have this extended lead ion, and you collide it with a single proton. So you test the quarks and gluons that are in the incoming lead ion, you test them locally. The reason for that is twofold. On the one hand, for the lead-lead collision program, you would like to know much better what you are actually colliding. What is it in the initial state that forms that liquid? And by testing this incoming projectile locally with a proton, you get such what we call benchmarking information. You get such information about what you are actually colliding. On the other hand, there is a fundamental theory of how quarks and gluons are distributed in a nucleon or a nucleus, how the quarks and gluons are distributed in this lead ion. And while we think normally that a lead ion is simply a collection of protons and neutrons, this is not true anymore if we look at the quark and gluon content. The quark and gluons cannot be assigned separately to a particular proton or a particular neutron, they interact across these protons and neutrons. So we have a specific idea from theory how in a high density incoming system of quarks and gluons these interactions takes place. And by colliding with a proton, we can test this fundamental idea, and we expect that there will be a qualitative differences to what has been accessible experimentally so far, and that these qualitative differences come from the fact that these lead ions are extremely densely packed in quarks and gluons. So the high density effects should be visible not only in the matter produced in heavy ions, but they should also be visible in the incoming ion. And that's what we want to learn. So two reasons: the benchmarking for the ion-ion collision program and the study of the partonic distribution inside the incoming ion projectile. So in both cases, in the proton-lead and the lead-lead collision, it is the center of mass energy, so the energy with which we collide these objects, that tell us which dimensions in the collision we can resolve. And what is important is that the dimensions we resolve are much smaller than the system size. And it is in this sense that we talk about material properties. Also, one could say this collision lasts only for 10 to the minus 23 seconds. It sounds like it's gone before we study it. However, the time scales of the processes are much shorter than these 10 to the minus 23 seconds. And it is in this relative sense that we can speak about matter properties. What is the real difference between a lead-lead collision and a proton-lead collision? That in a lead-lead collision, if we produce something in the middle, it has to plow through a large extent of matter before emerging in the vacuum. And it is this matter property that we want to study. While in a proton-lead collision, there is no such matter. It appears directly into the vacuum. So we can study what was produced without matter and compare it with the matter effects that we had in lead-lead collisions. And it is this difference that sharpens our understanding about the matter properties produced in lead-lead collisions. In fact, to add to my last point, let me just mention that there had been already a one-day proton-lead pilot run, as we said it. There are some first data, in particular the ALICE collaboration has made one publication of what is called a nuclear modification factor, and as the name says, this is a factor that characterizes the modification in a proton-nucleus collision compared to an equivalent number of proton-proton collisions. And the differences that one sees in this factor inform us already about some aspects of how the quarks and gluons in this incoming ion are distributed. So this was a very short run, and we expect to learn much more from more data, but in some sense these first data are already a proof of principle that the information I mentioned can indeed be extracted from proton-lead collision.